Uh, Good morning, everyone. Welcome to the third day of Linaro Connect, and thank you for having me here to talk about. My name is Grant Likely. I am a Senior Technical Director at ARM, and I'm the architect of the SystemReady IR or IoT Ready band. And today I'm here to talk about platform standards, how they apply to the rich compute embedded and IoT ecosystem. And I want to put forward the question, can embedded and IoT just work? We've talked about just work, we've talked about things being boring in the ARM server space, and that does an awful lot for enabling operating systems and really making for a richer ARM compute ecosystem. So we want to talk about how we can do that in other areas. Now, first of all, I just want to shout out to Linaro for this tool and how this conference is set up. I've been really impressed with how interactive it has been. Go ahead. I mean, I already see people doing this, but ask questions. I will try to leave some questions to answer questions at the end. But yes, please, anything that comes up, ask, and I'll try to answer them. So I want to talk about standardization. And if I'm talking about standardization, I have to start with how choosing standards is a balancing act to find the right fit for the ecosystems. Standards, they bring predictability needed to support for software to support ARM platforms. But if there's too much standardization, then we end up with a rigid platform and partners don't have the flexibility they need to bring products to the market. On the other hand, if we don't have standards or don't have enough standards, then that brings along a high software maintenance cost and engineering cost to port software onto the new platform. And then right in the middle, there's a balance there on choosing standards that enable innovation while also supporting interoperability. And we learned this really well when we started looking at doing ARM servers. In the course of that, we talked with our partners, we talked with silicon and software partners on what it is that they needed to be able to bring products to the market and support each other. And out of that came the Arm ServerReady certification program, which was based on a set of standards and testing to confirm that platforms met what was required by the operating systems. And really, we've had tremendous success with this. This is the expectation now of if you're putting together an ARM server platform that is going to run an off-the-shelf operating system, be that Windows or VMware ESXi or one of the enterprise Linux distros like SLES or RHEL, you have to be server ready. You have to meet these standards. So with that success, we started looking at what can we do to do that same thing and bring that same interoperability and just works to other ecosystems. And so late last year, we announced the SystemReady program. And the SystemReady program expands on the success of the ServerReady certification program. However, if we had approached this of taking what we did in ServerReady and just apply that over the entire ARM ecosystem, it simply wouldn't have worked, right? Because each part of the ARM ecosystem has different characteristics and different needs. So we needed to take a look at some specific places, determine what they need, and choose standards that are appropriate for that area. So what we have with SystemReady is instead of, we have one program that has multiple bands, each targeted at particular use cases and ecosystems. So I'm just going to go through these quickly. Over on the left-hand side, we've got SystemReady SR, or ServerReady, and this is simply the ServerReady program rebranded under SystemReady to show how this is part of the larger whole. Next one over is ES, or Embedded Server. And what we wanted to do with ES was take the success that we had with ServerReady with the shrink-wrapped operating system market and be able to run that or support that on a larger variety of ARM hardware. There are a lot of ARM SoCs out there that are performant devices that are great candidates for running general purpose software. And so ES takes the ServerReady standards, it relaxes some of the hardware requirements, but still allows the shrink-wrapped OSs to run. Next one over is IR, which is the primary one I'm talking about today, and that's IoT ready. So the IR program is focused on primarily the embedded Linux ecosystem and some embedded BSD as well as and other embedded OSs. But primarily, there is an embedded Linux ecosystem that is really healthy, and we needed to choose standards that made sense and fit well with what was already happening in the embedded Linux space. And then finally, there's one more band called LS, and that's Linux Boot Server, which is targeted for our hyperscale partners, for the platforms where they want to control the entire stack of firmware, and there's a definite preference for a Linux boot-based firmware stack, right? So within each of these bands, we can choose a set of standards that make sense within that. Now, if I back up a little bit further, ServerReady is part of a larger initiative that Arm's broader push into the edge and IoT infrastructure market. And this is our Project Cassini. Project Cassini is designed to ensure a cloud-native experience across a diverse set and secure edge ecosystem, and it operates across 3 vectors. The first vector is platform standards, which is where SystemReady sits. And these standards are a minimal set of features in silicon to support and firmware to support the OS or hypervisor. Second is security. ARM believes that all connected devices must meet key security goals and utilize a root of trust to ensure a baseline of security. So the PSA certified program builds assurance that devices have a security baseline aligned with key standards and use case requirements. In addition, the Parsec program is an open source project that provides cross-platform architecture agnostic APIs to provide those security features into applications. And then finally, there is the cloud native stacks. And so the Project Cassini aims to, well, as IoT market demands, they vary based on segment. So use cases, defining them is rather complex and involves secure gateways, aggregation devices, cloud platforms, connectivity, device and data management solutions, right? There's a lot of pieces that go into that. What Project Cassini does is it provides reference solutions that are developed in close partnership with the ecosystem and serve as building blocks for infrastructure and IoT edge use cases. If you want to know more about Project Cassini, you can contact us at ARM. There is a link at the end. But I'm going to move back and to talk specifically about SystemReady. Now, just like the ServerReady program, the SystemReady program is built on 3 things. It's built on hardware requirements, it's built on firmware requirements, and it's built on testing. Hardware requirements are defined in the base system architecture document, and this is, if you are familiar with the SBSA or server-based system architecture, we took that document, we reworked it, factored out the generic portions that apply to multiple bands, and created this new document. And this is the hardware requirements, how you should implement the ARM architecture, how you should connect up devices for maximum compatibility with OSs. Similarly, there's a firmware requirements document called base boot requirements, and this again is derived from the server base boot requirements from the ServerReady program. And this is the standard behavior consistent behavior that OSs and hypervisors can rely on to deploy onto and manage the platform. And the focus here is on the interfaces, not so much on the implementation. And then finally, if we've got these requirements, these are only really useful if we can test for them. So for each one of the bands of IR, we are producing an architecture compliance suite that tests the hardware features, the software features, and also yes. And so these are test suites that are open source. We're hosting them on GitHub, and this allows you to evaluate your platform for compliance before bringing it to certification, and then we use the same test suite for our certification evidence. And this goes across all the bands of SystemReady. But I've talked in very general terms. If we go and look at embedded, I need to start talking about specifics really fast. And so with SystemReady IR, I don't think it works to just come in with a set of requirements that are different, that are completely different or require a lot of changes from what already is there. So it's helpful to start with what I see in the embedded compute ecosystem right now. And there's some unique characteristics here. First of all, there's a huge amount of platform diversity. The embedded ARM compute ecosystem is very healthy. There are a lot of SoCs, there's a lot of partners producing devices, and you can see that ARM devices are everywhere. What that means, though, is that there's a lot of diversity in the implementations. A lot of vendor IP blocks, there's a low standardization on particular interfaces that are used. And these devices have to be highly configurable because they're used in a large number of different use cases. Second, there's a large amount of software diversity. Rather than a couple of major OSs that are the de facto standards, there's a lot of ways to build an embedded Linux device. And this goes everywhere from custom builds based on Yocto or OpenWRT, up to distros that have been taken and modified with maybe the kernel being replaced, and then third-party supported, whether we're talking Fedora IoT or one of the other products that are out there. And this isn't even discrete categories. This is a spectrum of different ways to land an operating system on a platform. Also, the OS images are tailored for the application. Each application requires a bespoke set of packages that have to be tailored to land on the platform. So we need to account for that in how this ecosystem works. And then finally, the incumbent projects here are U-Boot for the firmware project and Device Tree as the platform description. I mean, this is a large installed base. All of the SoCs have mature device tree support. There is significant engineering that's gone into the U-Boot ecosystem. And I mean, it's also preferred by a lot of us in the developer community. At this point, someone will invariably bring up, well, what about ACPI? Why aren't we just doing ACPI? And I mean, the reality is yes, we could use ACPI. There is significant work going on to bring up ACPI on embedded SoCs. But the pragmatic view is, at this point in time, ACPI simply isn't practical. There are a number of technical challenges to bringing up a high-quality ACPI implementation. So we don't want to get into a debate of whether it's ACPI or device tree, but for this particular band, we're saying device tree is the pragmatic and supported solution that you can build products right now with. And so device tree is what the SystemReady IR program is based on. Which I'm getting ahead of myself because I was talking about characteristics of the ecosystem. So SystemReady IR, this one's, again, tailored for embedded. And here's the vision of what we want, is regardless of what your device is along the bottom there, regardless of how you've designed your firmware, whether it's trusted firmware with U-Boot as the user space and Opti as a trusted OS, or just U-Boot in the normal world, or Tianocore in the normal world. All of these can present the same interface based on UEFI and device tree up to the OS ecosystem, so that if you're landing Yocto or one of the BSDs or one of the Linux distributions, all of those solutions can rely on consistent behavior from the platform and consistent description of the system, right? And so we acknowledge that while U-Boot as the primary implementation that's going to be used, there is choice here in how that's implemented. And in fact, if you implement a system with UEFI and device tree using Tianocore, or you've got an ES or SR certified system, we're able to use those the same interfaces to be compliant with IR. So let's go and talk about the specifics on what exactly is SystemReady IR. And I've got 7 points here, and these are the key elements that make for a compliant system. I'll go through these one by one. First one is UEFI. SystemReady IR is based on UEFI, and there is a subset of UEFI defined in the EBBR, or Embedded Base Boot Requirements document. I'll have a link at the end of the presentation. And that is a community developed document that's been driven by Linux developers and U-Boot developers of a subset of UEFI that is implemented right now. and provides everything needed by the majority distributions to boot on the platform. Right. So what UEFI brings is it brings consistency. The problems we've had with U-Boot in the past is while that is a very healthy and robust project, each platform that U-Boot lands on implements things slightly different, and it's hard to get a single image that's going to boot across the wide variety of platforms. So by standardizing on UEFI, we have consistent behavior that also matches the behavior of other UEFI platforms in the ARM ecosystem. Second, device tree, and specifically device tree that is provided by the platform firmware instead of carried along by the OS. And so to be IR certified, your firmware has to provide the system description so that the OS doesn't need to carry that system description along with it. Now, you might argue, I need to modify my device tree. I'm going to replace it. That's fine. The OS always has the option to provide its own device tree if that's your deployment model. But for compatibility, for system IR compliance, we want to have a default-based device tree in the platform so that there's a fighting chance of the OS being able to boot. Third, this isn't really a characteristic of SystemReady IR because we don't call out U-Boot or TFA, but the practical reality is everything for IR is implemented in U-Boot and TFA. You don't need to go and rejig your entire engineering process. What you can do instead is, as long as you're up to date on the firmware projects, you can turn on the EFI configuration, add the device tree to your platform, and you've got most of the things that you need to be IR compliant. Related to that, a new addition to EBBR is update capsule is required. And what update capsule does, well, okay, we at ARM, I mean, if we're building secure, always-on connected devices, in order for those always-on connected devices to remain always-on connected and secure, you really need to be able to update all the components, and that includes the firmware. But with traditional embedded stacks, each platform has a slightly different way of updating firmware, and the OS needs to know details on where it's supposed to write its firmware. What Update Capsule does is it brings a consistent API so that firmware knows how to write firmware images to flash, and the operating system is able to discover what firmware images are available with the ESRT table, and then use Update Capsule to actually write it into the system. So this again provides that consistency. Next, compliance testing. To be certified, we go through compliance testing, and we've got a process that we can work through with you as our partners on bringing your platform from enabling all these features, testing it yourself, and then having us confirm that and giving you a certification. Next one works with the Yocto project. Again, kind of like the U-Boot and TFA one, this isn't actually called out in SystemReady IR, but I really want to highlight it that this isn't just about binary distros being able to work on embedded SoCs. This is also about custom build, Yocto, OpenWRT, build root, or any other method that you use for building your OS. And the key here is consistency. Is you can build a Yocto image that will very easily deploy on multiple platforms without having to do a separate image for each platform. There was a presentation on Tuesday that's called this specifically out, that having to build Yocto images for each and every platform is a very expensive affair. So you can build multi-platform images with Yocto quite easily if everything is IR compliant. And then the last one is that you must test against top-tier distros. The goal here, again, is consistency, compatibility, and we use the top-tier distros as evidence that the platform conforms. You might ask, why do I even care about that? I'm planning to use Yocto or something else and do a custom build, which is totally fine. But in terms of certification, we use the top-tier distros, whether it be Red Hat, Fedora, SUSE, or Ubuntu, to provide evidence that these really are conforming platforms. Okay. And then the last thing that I want to bring up, which isn't actually, it's not part of System IR proper, but there is kind of an add-on certification that can be for security or secure boot, which is based on the BBSR, or Base Boot Security Requirements document. And this is if you implement UEFI secure boot, there is additional testing that we can do to say that that is implemented correctly. This isn't required now, but really IoT connected devices need to be secure, so this is really important to pay attention to. And then this just shows that IR, it is part of the larger SystemReady program. These are not different standards that we've just plucked out of thin air, but across, when you look at IR compared with ES and SR, they're all based on UEFI. They all run on 64-bit ARM. IR also gives you the option on 32-bit, where that's not so much on ES and SR. And then, while IR is based on device tree, ES and SR are on ACPI and SMBIOS. And that is the most significant difference between the two. Now, it's also worth pointing out, and I've said this already once, is that between IR and ES, there's actually quite a few SoCs that can land in both cases. So which one you choose depends on what you care about. If you care about if you only care about embedded Linux, IR has lower requirements and it is easier to implement. Whereas ES gives you access to a much broader range of software with Windows and VMware as examples of ones, and Enterprise Linux. So that's a choice to make when you're looking at certification. And as you can see, we've already got quite a few partners. We have certified platforms under the SR and ES bands. We don't have any certified under IR yet, but that's because it's a new program. And so we're bringing that up now, and you can expect to see certification announcements in the coming months. Current status, the documents that you need are all released. You can go to developer.arm.com to find out more. We've got some example platforms that we are working on. And we also are in the progress of writing some how-to documentation on actually implementing this. But most of what you need is already out there in open source. So to sum up, we're spinning up the certification program now. You can expect announcements later this year. Join us on the EBBR community in GitHub, or contact us about certification at systemready@arm.com. And then I also just have to highlight some of the sessions that have already come up at Linaro Connect. There's been SR, ES, and IR sessions on Tuesday. I'm not sure when the recordings will be up, but you can go and look for those. There was a case on UEFI boot on IoT devices, standard firmware update, and also the generic image approach on the Ledge reference platform, which leverages an IR. And that is that. So are there any questions? I see one. So is the SR IR requires device tree or tolerates device tree? So I already talked about that we've got device tree is required. I'm just checking anything else. So I am not, nice. Okay, and it looks like there's been some answers to questions right now. Francois, you mentioned EBBR does not require a specific system description language. That is correct. So EBBR is ACPI or device tree, and that is fine. But for the SystemReady IR certification program, we are specifically requiring device tree because that's what that ecosystem is expecting. If you have ACPI in your platform, rather than doing an IR certification, we're encouraging you to go and look at an ES certification because that gives you access to a wider range of OSs, and presumably that's why you would have implemented ACPI. The reason that language is in EBBR is we want to make sure that it's possible to build a system that is both IR and ES compatible. And I think that is it. I'm not seeing any other. One more. So generic IR compliant Yocto image, presumably that means all BB append and various SoC BSP layers that patch all manner of things need to go away. There is a meta ARM that we're looking at making sure it implements everything that's needed. I don't know enough about the Yocto layers to answer that specifically, but yes, if you're building a generic image, you would want to do away with anything that is exclusive for a single platform and try to do add-on pieces into that. And at that, I am out of time. So I'm going to say thank you very much and enjoy the last day of Connect.